He's of course, he needs no introduction. He's one of the giants of the field. So John is a theorist, but I think his work has reached out in many ways to both the foundations of physics as well as to more practical quantum computing. You know, between his work in error correction and quantum gravity and NISQ devices, and so you know, obviously today is probably reaching out more towards the practical side. I should say one thing that's really remarkable about John is that I think an astounding fraction of the people in the field, especially on the physics side, have been mentored by him. So, John, looking forward to your talk.
All right, thank you, Umesh, for the kind introduction. I guess I can't resist mentioning that an astonishing fraction of people in the field on the computer science side have been mentored by you. I'm going to talk mostly about some work I've done with Robert Huang and Richard Kuhn. My collaborators are far more knowledgeable than I am about machine learning and probability theory. This has been a very illuminating and exciting collaboration for me. And in the second half of the talk, I'll say some things about some work we're currently doing, joined by Victor Albert and Giacomo Torlai. So the theme is classical shadows of quantum state. So what does that mean, and why should we care about it? Well, what I want to describe is an efficient and experimentally feasible way of translating a quantum many-body state into succinct classical language while retaining, with that classical description, the ability to predict many useful properties of the state. Is that useful? We're in the NISQ era. We are aspiring to achieve quantum advantage in platforms, perhaps in the next few years. And perhaps our best hope for doing so is by means of hybrid quantum classical algorithms to use our classical computers to the extent that we can, and then boost their power with quantum devices used as co-processors. So if it's experimentally feasible to trade quantum for classical resources while not compromising our ability to carry out an application, it's likely to be beneficial to do so. And with these classical shadows, we can improve the efficiency of variational methods for solving optimization problems. And by converting from quantum to classical language, we can then use classical machine learning tools to address quantum problems. So what we're shooting for is some tractable way of translating from quantum to classical data. Specifically, we would like, if we have a quantum many-body state in our quantum device, to be able, with a small number of measurements, which are easy to do experimentally, to obtain this classical description from which we can predict many properties of the many-body state. We want that classical description to be succinct and easy to store, and we want our predictions to be easy to do by classical computation. And we want a rigorous guarantee that our predictions have a small error with high probability. The kinds of properties we might want to predict are fidelity with target states, or expectation values of a local observables, or few point correlation functions, or entanglement entropy. And the types of resources we'll care about is how difficult is it to do this translation from quantum to classical on our quantum platform? How many copies of the quantum state will we need to be able to make accurate predictions? How much classical memory we'll need, and how much classical processing to derive those predictions. So as you know, there is a procedure for translating a quantum state into classical language, doing full quantum state tomography, and then we can use that classical description to derive properties of the quantum state. But full quantum state tomography is very inefficient for many-body systems. The description itself is exponential in the number of qubits, the system size, The number of samples that we need to extract accurate predictions is also exponential in system size. The amount of classical storage and classical processing we need to do to compute predictions is also exponential. So that's not a practical procedure for systems with many qubits. There is the ingenious idea of shadow tomography, which Scott developed and analyzed, where one doesn't try to learn a complete description of the quantum state, but the goal instead is to make accurate predictions for expectation values of some set of operators. And remarkably, in that case, it turns out the number of samples that we need to make those predictions scales polynomially with the system size. And furthermore, in order to predict M properties, we only need a polylogarithmic number of copies of the state. However, this is still not a practical procedure because it requires very expensive quantum processing, including quantum computations that act across multiple copies of the state, and a lot of storage and post-processing to make predictions. There are also heuristic ideas for extracting predictions from quantum states, like neural network quantum state tomography. One can perform some set of measurements to train a neural network, which can then be used to predict additional properties of the state. And in practice, that may work well in some instances. And furthermore, the quantum experiments that we need to do to train the neural network are feasible, but we don't really have a rigorous theory of neural network quantum state tomography. It's a heuristic procedure. And so we can't say in general for some input quantum state, how many samples we'll need, how much storage and how much processing in order to get good predictions with high success probability. So what we'd want is a procedure where we can prove that it's efficient, both in terms of the quantum processing we need to do on the input state, the amount of classical storage we need, and the amount of classical processing we need, which will enable us to learn some classical representation of an unknown input state from a small number of measurements, and then use it to predict many properties of the state. And the result that we proved about a year ago shows that this is possible under certain conditions. That if we want to predict expectation values of a list of M observables, and to do so with a small constant error with a high success probability, then the number of copies of the state that we need to do, the number of repetitions of the experiment, is just logarithmic in the number of properties to be predicted. But there's a catch. There's a prefactor here, which depends on something I've called the shadow norm. And we require all of the operators to have a sufficiently small shadow norm. I'll explain what I mean by the shadow norm later on. But it turns out, for some cases of interest, that the shadow norm is actually a constant independent of system size. So in that case, we're saying that we can predict M properties with of order log M measurements, and the sample complexity that we need doesn't depend on the system size at all. The experiments are efficient on the quantum platform, and the classical storage and processing are also reasonable. If I wanted to just naively measure M different observables one by one, I would need a number of copies of the state in the millions, but we're saying that we only need a few times the log of M copies of the state to get accurate predictions with high success probability, a big improvement. So let's see how this procedure works. Let's say we have N copies of the state, and so we repeatedly do experiments on the state in the following way. There are a number of variants on the procedure, but they all have in common that it's a randomized protocol, and there's some ensemble of unitaries that we can choose from. And in each run of the experiment, we select a unitary from that ensemble. We want this unitary to be something we can really do in the lab, and we also want it to be something that we can describe succinctly in terms of classical data. We apply that unitary to the system, and then we measure in the computational basis. If it's an n-qubit state, we collect n bits of data in doing so. And then we obtain a snapshot of the state, which is the result of applying the inverse of the unitary to that measurement outcome. And this is something that I do acting on the classical data. The unitary is something I can efficiently describe and invert. And so I can apply that unitary to the bit string to get this snapshot. And the full collection of all n snapshots is what I'm calling the classical shadow. So let's note for later reference that if I consider averaging over all the unitaries in the ensemble, and also averaging over the measurement outcomes, that defines some channel acting on the input quantum state, some CPTP map. So again, what we were going to want to do is we have this very complex quantum beast in the lab. And what we do with it time after time is we apply some unitary chosen from our ensemble, and then we do computational basis measurement. That gives us a snapshot, and then we do it again and again. And that collection of snapshots is the classical shadow. So to make it even more concrete, let's suppose, for example, that I have some quantum state which lives on the equator of the Bloch sphere. And our ensemble of unitaries is the identity and a 90-degree rotation about the z-axis of the Bloch sphere. So depending on that choice of unitary, I'm either measuring in the computational basis 0 and 1 or in the x basis plus or minus. And for this particular state, when I measure in the z basis, I'm more likely to get a 0, less likely to get a 1. If I measure in the x basis, I'm more likely to get a plus, less likely to get a minus. But the snapshots are 0 or plus or 1 or minus, depending on the outcomes of the measurements. And if I average over the choice of measurement and also the outcomes, that defines a channel, which is just a depolarizing channel, which preserves the state with some non-zero probability and replaces it with a completely mixed state with the complementary probability. So that defines a channel which causes the state to sink towards the origin of the Bloch sphere, but without sinking all the way to the origin. Okay, so we have all these snapshots. What should we do with them? Well, we store the snapshot succinctly in a classical memory. And as I said, averaging over the ensemble of unitaries and the measurement outcomes defines some channel. If our measurements are tomographically complete, that channel will actually be an invertible matrix. It's not invertible by a physical map that we can do in the lab. And in fact, it takes the snapshot to an object which is not a physical density operator. But that's okay, because we don't want to invert this channel in the lab. We just want to invert it in our classical memory by doing some classical processing. And we can do that. And then if we average over the choices of measurement and the outcomes and apply the inverse of the channel to each one of the snapshots, the expectation value will be the input density operator itself. So if we repeat the measurement many times, we have a good unbiased estimator of the state. But in order to be assured that we can make good predictions, we have to know something about the variance of our estimator. But here's what we're going to do to make predictions. I have some set of operators, which let's say I can describe succinctly, classically. And then for each one of those operators, I compute its expectation value in the result of the inverse of the channel applied to the snapshot. Now, even if I know the variance, if I don't know anything else about the distribution, I have to worry about our predictions being corrupted by rare large deviations from the mean. But there's a trick for dealing with that called median of means estimation. I can take our estimates and divide them up into many bins and compute the average of the estimates in each bin. Each one of those gives estimate of the expectation value of the observable, but where a large deviation might occur. But then I take the median of all the estimates. And then in order for that median to deviate badly from the mean, we would have to have a large deviation in half of the bins. And that becomes exponentially unlikely as we increase the number of bins, exponential in the number of bins. So once we have a sufficient size sample, we can have the probability of a large deviation under control. And in fact, that's what enables us to guarantee that with high success probability, we can predict a number of observables, which is exponential in the number of repetitions of the experiment. But the shadow norm comes in when we attempt to estimate the variance of our estimator. So far I've described the procedure abstractly. To be more concrete, we should consider particular ensembles of unitaries. So suppose we sample those unitaries uniformly from the Clifford group. So then the procedure is I select a random Clifford transformation, and then I measure all the qubits in the computational basis. That's equivalent to simultaneously measuring a randomly selected set of commuting Pauli operators. And I do that many times. Now, the channel that generates when we average over the Clifford transformations and the outcomes looks like this, averaged over unitaries to averaged over outcomes. And it's an expression which is quadratic in the unitary U and quadratic in its adjoint. But the Clifford group has the delightful property of being a unitary two design. So I can replace that average over Clifford transformations by a uniform average using harm measure over the unitary group. And averages over the unitary group are easy to compute because the only things that survive are unitary invariants, which we can characterize and compute explicitly. So it turns out for this Clifford measurement scenario, the corresponding channel is a depolarizing channel with some probability of preserving the state, some probability of replacing it by the maximally mixed state. And that's a channel that we know how to invert. Now I want to compute the variance of our estimator. I can use the property that this inverse of the channel is a self-adjoint operator, so I can turn the M inverse acting on the snapshot into an M inverse acting on the operator. And for the variance, I get an expression that looks like this, where now there's a square of this piece. So there are 3 U's and 3 U adjoints in the expression, which I need to average over the Clifford group. But the Clifford group also has the delightful property of being a unitary 3 design. So in this case as well, we can replace the averaging over the Clifford group by averaging over the unitary group and get an explicit estimate of the variance, what we call the shadow norm. And then we can optimize that overall or maximize it over all possible input states. And that's how we estimate the shadow norm. And in this case, it's just a constant times the Hilbert-Schmidt norm. An example of an observable that has a constant Hilbert-Schmidt norm is finding the fidelity with some target pure state. We'd be interested in the case where we can succinctly describe that target pure state. So what I'm saying in the case of fidelity estimation is that I can repeat my experiment all together n times, and then I can, with some small error and a high success probability, compute the fidelity with an exponential in n number of target states, and the number of copies that I need doesn't depend on the system size at all. Now the trouble is that although Clifford transformations are nice, they're still a little too hard to do in current quantum platforms since they require circuits of sufficient depth. We need a circuit size which is almost n squared. We'd like to have something simpler that we really can do experimentally. Well, what could be simpler than this? We just take each one of the qubits and decide uniformly at random to measure one of the Pauli operators, x, y, or z. So I call that Pauli measurement. And in this case as well, it's easy to see what the channel is because this is really equivalent to doing the single qubit Clifford group and then performing a computational basis measurement. And again, averaging over the Clifford group is the same as averaging over the unitary group. Now we have a tensor product of depolarizing channels acting on the n qubits. That's easy to invert. Then we can estimate the variance. That's our shadow norm. Use the property that the single qubit Clifford group is a 3 design to get our estimate. And what we find in this case is that we can relate the shadow norm to the operator norm of the observable that we're trying to predict, but there's also an exponential dependence on the weight of the observable, on the number of qubits on which it acts non-trivially. But we can make good predictions efficiently if we're interested in observables which have constant weight, like if we were computing local observables, sums of local observables, 2-point correlation functions, and so on. Now, this procedure works for estimating arbitrary observables of constant weight, but to get some intuition concerning why the cost grows exponentially with the weight, we can consider the simpler special case of just predicting Pauli operators, expectation values of Pauli operators. So if we have some list of Pauli operators that we want to be able to protect or want to be able to predict, and they're all of constant weight, weight no larger than W, here's one of them, XZZX, acting on some subset of the qubits and acting trivially on the rest, then we do our randomized procedure and we have some non-zero probability of hitting the right Pauli operators for, in this case, the 4 operators on which we have a non-trivial action. And that probability of hitting the right Pauli operator will go like 3 to the minus the weight, if the weight is W. And in this case, we don't have to bother with median of means estimation because we know how to characterize the variance of the estimator directly. But it turns out then that we need to repeat the experiment in order to predict operators of weight no larger than W a number of times that scales like 3 to the W, but we can predict a number of Pauli operators, which is exponential in the number of repetitions of the experiment. And that was nicely discussed by these guys before we did our work. Now, that procedure applies to arbitrary lists of Pauli operators, but it's often interesting to consider Pauli operators that have some special structure we can exploit. And then we might be able to do better with a deterministic procedure. We can arrive at such a procedure just by de-randomizing this randomized Pauli measurement procedure. So let's say we have some list of Pauli operators, each acting on n qubits, and the randomized protocol gives some guaranteed performance with high probability on our concrete list of Pauli operators we want to predict. What we can consider is fixing one of the Pauli measurements to be X, Y, or Z, and then see how the procedure performs when we randomize the measurements on the rest of the operators, and we can choose the choice X, Y, or Z for that particular qubit and that particular Pauli operator to give the best performance. And we can do that iteratively since we can compute bounds on the performance efficiently. We can efficiently step through our list of Pauli operators 1 qubit at a time, and each time replace the randomized Pauli measurement by some fixed Pauli measurement and continue to randomize over the rest. And then when we've stepped through the whole list, we completely de-randomize the procedure. And here's an example of a case in which that helps. This is inspired by an actual experiment that was done by the Innsbruck group a couple of years ago with an ion trap with 20 ions. They were specifically motivated by studying electrodynamics in 1 dimension, but for our purposes, we don't have to worry about that. This is really a spin system, a set of qubits where the Hamiltonian is a sum of 2 qubit operators, but without a geometric locality constraint. So the Hamiltonian has of order n squared terms in it. And then they did a very clever thing in this experiment. They did a variational search for states which have low energy, but they also search for states that have a low value of the variance of the Hamiltonian, searching for the case in which the expectation value of the Hamiltonian squared is close to the square of the expectation value of the Hamiltonian. When that variance is small, it means we're close to having an eigenstate of the Hamiltonian. So starting with some initial state and carrying out this variational procedure, we can find not just the ground state, the lowest energy state, but other low-lying energy eigenstates, and that's what they did. But this is a pretty expensive procedure. The Hamiltonian has order n squared terms. The Hamiltonian squared has order n to the fourth terms. That's a lot of Pauli operators that we need to predict. And in the experiment, they handcrafted a procedure for extracting the expectation values of Pauli operators that they needed to find the variance of the Hamiltonian. And actually, their procedure does better for modest system size than the classical shadow procedure. But as the system size grows, in the case of the classical shadow protocol, we're trying to estimate of order n to the 4 Pauli operators, but the number of experiments that we need just grows logarithmically with that, while their procedure actually has a dependence which is linear in system size. So classical shadows do considerably better for large system size. But there's enough structure in the Pauli operators in this case that we can get a big gain by de-randomizing. So if we de-randomize the Pauli measurement the way I described, we can get a big reduction by about an order of magnitude in the number of experiments that we need to do to get a desired error. We also looked at some applications to quantum chemistry. This is a case where the classical shadow method might be challenged because a quantum chemistry problem is a problem in electronic structure. It's a Hamiltonian for a system of fermions, and we have to encode that in qubits. And when we do so, some of the Pauli operators that arise have relatively high weight, which means that might be disadvantageous for the randomized protocol. This is an indication of the performance of the classical shadow method, indicating the error in the estimation of the ground state energy for some particular benchmark molecule, where it can be described by a small enough number of qubits so we can do exact diagonalization so we know what the right answer is and we can test our procedure for that benchmark example. The IBM group pointed out that you can actually do better because you can put some bias into the classical shadow protocol. The Pauli operators that arise are more likely to be supported on X than on Y and Z. So we can, instead of using a uniform distribution on X, Y, and Z by biasing the distribution, we have a better chance of hitting the Pauli operators that we're interested in. But if we take the classical shadow protocol and we de-randomize it, then we can do considerably better. And with a smaller number of experiments, get to the desired error. Now, I've been talking about predicting expectation values of operators, linear functions of the density operator. But I should emphasize that we can also estimate nonlinear functions. In fact, if I want to compute a function which is quadratic in the density operator, we can just think of that as the expectation value of an observable in the state, which is the tensor product of two copies of rho. And we can use classical shadows to estimate that quantity by taking pairs of snapshots and replacing the first copy of rho by one snapshot and the second copy by another distinct snapshot, and then average over all the ways of choosing the pairs of snapshots to get our estimate. And in that case as well, we can do an estimate of the variance of the estimator and get some performance guarantee on our predictions. We can use that, for example, to estimate Renyi entropies of subsystems. And in a collaboration with the Innsbruck group, we applied that to studying entanglement dynamics after a quench in an ion trap experiment. The cost of estimating the entropy of cost of a subsystem still grows exponentially with the number of qubits in the subsystem. We can't get around that. But the classical shadow procedure does provide a more efficient way of estimating Randi entropies than previously used randomized measurement protocols. So now I'd like to talk about something we've been thinking about lately, which is applying machine learning to quantum problems. And this is something that has attracted a lot of attention the last few years, and there are promising results. But most of what's been done is heuristic, and we were interested whether there are situations in which we can show that machine learning used to solve a quantum problem really does work efficiently. And we found a couple of settings in which that's true, which I'll explain. The first setting is the problem of learning properties of a quantum ground state. So let's suppose that there's some family of Hamiltonians. They're all local Hamiltonians in some finite dimension. And we're guaranteed that there's an energy gap, a constant gap between the ground state and the first excited state for all the Hamiltonians in the family. They are smoothly parametrized by some set of real parameters. There may be many real parameters. It could live in a high dimensional parameter space. And what we want to do is predict properties of the ground states for various values of x. During the training stage, we're going to suppose that we are provided with a sample of the ground state for some value of x that we want to sample from. And that's something that, of course, would have to be prepared on a quantum platform somehow. And our goal is, after training, to predict properties of the ground state for new values of x beyond those that are encountered during training. So, for example, we might want to learn the expectation value of some sum of local operators in the ground state at that new value of x. And the idea that we studied is to convert the training states to their classical shadows and to train on the classical shadows. And then during the prediction phase, we don't use the quantum platform at all. Rather, we're given some value of x and a description of the local Hamiltonian. And then we want to use our classical learning algorithm to predict the classical shadow for a new value of x. And then that classical shadow can be used to predict many properties of the ground state for that new value of x. It turns out that this learning really is efficient. We can get by with an amount of training data which scales reasonably with the system size and with the dimension of the parameter space, if we're assured that the properties that we want to predict do not vary too rapidly as a function in the parameter space. And we can actually prove that that's true for the case of expectation values of local operators in the ground state of a finite dimensional gapped local Hamiltonian, or in fact for any state as a function of x, which is spectrally isolated from other eigenstates throughout the parameter regime, that guarantee that the function varies slowly is obtained using the method called quasi-adiabatic continuation or spectral flow. But once we know it's true, then we're assured that this prediction procedure is really efficient. All the learning is classical. We learn using the classical shadows as inputs, and we predict classical shadows for the new values of x, but we still need the quantum platform to somehow prepare the ground state for the values of x encountered during training, and to extract the classical shadow by measuring the ground state. So we've done some numerical experiments to see how well this works. Here's one example. It's an example chosen because it corresponds to a system studied in a real experiment. It's an array of Rydberg atoms, altogether 51 atoms held in a tweezer array in one dimension. You don't have to worry about that so much. You can just think about it as a system with 51 qubits with a Hamiltonian that, aside from the overall scale, is parameterized by two real parameters. And as we vary these parameters, as we increase one of those, that favors that the qubits take the value 1 over taking the value 0. But as we increase the other parameter, that disfavors two ones sitting at neighboring sites in the chain or even nearby sites in the chain. So there's a competition between those two effects, which gives rise to an interesting phase structure, as I've indicated here. So what we do is we select some points in this parameter space. That's our training data. Those are the points that are shown by circles which have the dark boundary around them. They're altogether 20 such points selected here. And then after training, we want to predict properties at new values of the parameters. And those are the ones indicated by the cross, the diamond, and the star. Now, in this case, it's 51 qubits, but it's a one-dimensional chain. So you can use DMRG to compute accurately the exact properties of the system and estimate in particular, using DMRG, the expectation values of local observables. So we know what the right answers are, and we want to test how well our training procedure performs. So we can use the classical shadow after training to predict a variety of different local operators, but just to get an idea of how it works, let's say we want to predict site by site the expectation value of the Pauli operator Z. For the point indicated by the diamond, you can look here, and the solid curve is the right answer that we get from the DMRG calculation. And the diamonds are the predictions that come out of our prediction model. And you can see they match up with the DMRG results pretty well. If we did something more naive, if we tried to predict at the diamond point just using the closest by point in the training space, then we wouldn't do very well at all. That's shown in the next plot. It's the same DMRG data, but here is the data from the neighboring point, which doesn't match up with the right answer very well. And here, similarly, we can look at the point indicated by a cross. This is actually in the phase of the system where ones and zeros want to alternate in the ground state, 1, 0, 1, 0, 1, 0. And so when we look at the expectation value of Z, we see these oscillations. Again, the solid curve is the result from DMRG, and the crosses are the result from the prediction model. And if we just use this nearby point to try to predict, we don't do very well at all. So the prediction model really is leveraging the results from the training sample beyond just the points which are closest by. Now, the truth is, in this case, our rigorous theory does not directly apply. It doesn't guarantee that we'll get good predictions. And the reason is that there are phase transitions in this parameter space. The theory applies if we have a constant spectral gap throughout the parameter region that we're sampling from, and that's not the case here because there are really 3 phases. But we find, nevertheless, that the predictions work pretty well, even though some of the training data is coming from other phases. That wasn't guaranteed to work, but it works pretty well. The other thing I'd like to discuss is using machine learning to identify quantum phases of matter. So the idea here is that during training, we are offered samples of quantum states which are representatives of either one of 2 possible phases, let's say A and B. And those samples that we have during training are labeled. So we know which ones come from phase A and which ones come from phase B. And then after training, Our goal is when we encounter a new quantum state that doesn't carry a label, we are supposed to predict that phase label with good accuracy. Again, the idea is to take the quantum states that we encounter during training, convert them efficiently in our experimental platform into a classical shadow, and then to learn to classify the shadows. And then during prediction, when we have a new quantum state, we convert it to its classical shadow, and then we try to assign the right label to the shadow. The procedure we apply to learn here is kind of a standard scenario in learning theory. We take the input data during training and prediction, and we map that to a high dimensional feature space. But the input data here is not the quantum state itself, but its classical shadow. And then in this higher dimensional feature space, we try to find a linear classifying function, a hyperplane in the feature space that separates the data from the two phases, with phase A points on one side of the hyperplane and phase B points on the other side. And if the points from either phase don't come too close to the hyperplane, then it's relatively easy to learn that linear function that classifies into phases. Now, to show whether this will really work, we need an assumption, which is physically motivated, and that is that there is some classifying function that can be used to identify phases, which is a polynomial in few-body marginal density operators. We don't have to know that function in advance. We're going to learn it. But to guarantee that this procedure will work, we need to know that it exists. When the type of thing I might be interested in is distinguishing a trivial phase from a topological phase. And it's often said that in order to identify a topological phase, I need some kind of nonlinear, or sorry, some non-local order parameter to identify it. What really happens, though, is as long as the correlation length is finite in the topological or trivial phase, then we can look at a volume, which maybe is a little bit larger than the correlation volume, and that already suffices to distinguish the two phases. An example of that would be in the case of a topological phase, we can compute something called the topological entanglement entropy, which has somewhat different scaling than entropy in the trivial phase. So we can tell the difference, and that scaling already kicks in when we consider subsystems with a size larger than the correlation length. So we have to assume that such a classifying function exists, but if it is, we can build our feature map so that it's guaranteed the learning will be efficient, meaning the amount of training data and the classical processing that are required are polynomial in the system size. As we get closer to a phase boundary, what we expect to happen is that we have to look at larger and larger subsystems in order to distinguish the phases, and then the learning gets more and more difficult. But for a fixed correlation length, we can efficiently learn to distinguish the trivial and topological phases, for example. So again, we did some numerical experiments. In particular, the case of trying to distinguish the trivial phase from the toric code topologically ordered phase. Now, what it's one way of defining what you mean by topological order is that it's not possible, starting with a trivial state, a product state, to create a state in the topologically ordered phase with a local circuit that has constant depth. Now here, of course, we're considering some finite system size, so exactly what you mean by constant depth is a little murky. In the numerical experiments, we considered the toric code on a 10 by 10 lattice. So the code distance is 10, they're 200 qubits. And we can take the exactly solved Kitaev model as a representative of the topologically non-trivial phase. And then we can consider applying some low depth circuit to that state to get some other representative of the topological phase. And likewise, we can start with a representative of the trivial phase, a product state, and apply some local low depth circuit to that. And then what we expect is that if the circuits are of sufficiently low depth, we will be able to classify the states to tell the difference between the topological and trivial states. So what's shown over here on the left is that we take the feature space to which our classical shadows are mapped, and we project the geometry of that feature space down to a few dimensions, 2 dimensions in this case. And you can see that the representatives of the topological phase are well separated from those in the trivial phase. So it's not that difficult to learn a linear function to find a hyperplane that separates them effectively. What's shown over here on the right is, as we increase the circuit size, how the distinguishability between the two phases is compromised. This is actually just projecting down to 1 dimension, but with the data arranged in a way that gives you a visualization of how the data is distributed in that 1 dimension. So remember, I'm talking about the case where the code distance is 10. The case where I have the 0 depth circuit applied, that just means I have Kitaev's toric code and product state. And those are easy to tell apart when we take their classical shadows. But then as we apply circuits of increasing depth to both the topological state and the trivial state, the ability to distinguish gets worse and worse. And when the data here is actually shown for the case where the circuit that's applied has depth 3, we can still separate the two pretty well. But by the time we get up to a depth which is about half of the code distance, then our ability to predict is being badly compromised. Okay, so our main results from studying applications of machine learning to quantum problems are summarized here. One theorem concerns learning the properties of ground states. A statement is that for any smooth family of Hamiltonians, in a finite spatial dimension, they're local Hamiltonians, I should have said, where there's a constant spectral gap, there's a classical machine learning algorithm which can learn to predict an efficient classical representation of the ground state that can be used to approximate few body reduced density operators up to a constant error. And the amount of training data and the computation that we need is polynomial in the dimension of the parameter space and linear in the system size. Now, the procedure is that during training, we take the input states, we translate them into classical shadows, and we actually train on the classical shadows. And in the prediction phase, we don't use the quantum platform at all. Rather, we predict for a new value of x what the classical shadow is, and then we can use that to predict properties. And the second result concerns identifying quantum phases of matter. And it says that if there exists a polynomial function of few body reduced density operators that does classify phases, then there's a classical machine learning algorithm that can learn that and can predict phases accurately. And the required amount of training data and the computation time are polynomial in the system size. And again, the procedure is to take an input state during training or prediction and to translate it into a classical shadow. And we learn to classify the classical shadows during training, and then we can predict the correct label when we get new input classical shadows in the prediction phase.
Hi, John. There's a question on the Q&A about this. So Frederick asks, is there some direct connection to those ground states obeying an area law and being in principle representable by a tensor network?
No. So actually, here's an important point. We can learn properties of ground states by using the training data, which would be hard to learn if we didn't have the training data. So if we only had the description of the Hamiltonian and we tried to construct an approximation to the ground state and use that to predict properties, that might be a very hard problem. But what we're learning is that if we have a quantum platform which provides us with samples of the quantum state, then by measuring those and by doing measurements that are not so difficult for a real quantum platform, then we can proceed to make predictions about the properties of Hamiltonians in this parametrized family, even though we couldn't do that directly without making use of the quantum platform. In fact, we did the following thing just to illustrate the point. You can encode in a quantum state a solution to a factoring problem. And you can choose that to be a ground state of some suitable local Hamiltonian. And furthermore, because we can use Shor's algorithm, that state could be easy to prepare in a quantum platform. And now we now are given samples of that easy to prepare quantum state, easy to prepare on a quantum platform. And by measuring them and then training on the classical shadows, we can actually solve the factoring problem. But we were able to do that because it was encoded in the quantum state itself. So that's an illustration of how by training on this classical data, we can do things that we couldn't do if we didn't have access to the quantum platform at all. I think I was done with this slide, right? Okay. Actually, I'm done with the talk. So here's a summary. So I've told you about classical shadows of quantum states. This is a procedure which is actually feasible in the lab for translating a state from quantum language into succinct classical language. And that classical data can be easily stored, and by doing efficient processing, if we consider some list of properties that have satisfy a suitable criterion, then we can predict accurately with a high probability of success and properties with just measurements of order log m copies of the quantum state. I didn't actually talk about this, but we can show that the number of copies is actually asymptotically optimal if we're limited to measuring the states one at a time. We can do better if we can make entangling measurements across multiple copies, but that would be much harder to do with the quantum platform. The sample complexity and the classical processing time for making predictions can improve on methods that have been used previously. And with classical machine learning, combined with classical shadows, we can effectively address some quantum many-body problems. Now, this talk has been about making predictions, and I'll predict that classical shadows will be used fruitfully in the years ahead to develop further applications of near-term quantum platforms. So thanks a lot for listening.
Great, thank you. That was a fantastic talk. Let's see if there are any more questions. So Adam or Anurag, do you?
Yeah, I see Soonwon has a question. You can go ahead and ask it directly.
Thank you for nice talk. Sorry, can you hear me?
Yeah, I hear you.
Yeah, I have a question about the learning the properties of the ground state. So unlike the shadow tomography, in order to predict the property, you need to somehow interpolate or extrapolate within the parameter space of the Hamiltonian. In your case, is X. So could you explain how you smoothly interpolate those data from the shadow tomography method?
How we smoothly interpolate the data? Well, as I said, we need the feature that the properties that we're going to predict with the classical shadow actually have some bounded gradient as a function of the parameters, which label the family of Hamiltonians. So really what we do is Fourier analysis. Knowing that bound on the gradient, we can reconstruct the a smoothed version of the classical shadow in which we throw away very high wave number Fourier components. So the number of Fourier components that we actually need to learn is a reasonable number. And that's why without a lot of training data, we're able to learn a good enough approximation to the classical shadow that we can make predictions.
Mm-hmm. Thank you.
Great. Yeah, I see. Maybe next, Ehud, you want to ask your question? Cool.
Yeah. So this might be a bit outside your theorem, but what do you feel about that? So, if your wave for the machine learning phases, if your wave function was not generated by a deterministic Hamiltonian, but by some stochastic process, so you had one shadow for each wave function, but you could still classify the states that you get, whether they're in the topological or say trivial, they're topological or trivial. Would you still be able to use this method, do you think? Or
well, I'm not quite sure what you mean, because there's not really a Hamiltonian in the training task. There's just a bunch of states, and we're trying to classify the states. So
yeah, but what you need to give instead of a Hamiltonian is there is a stochastic process that is parameterized by some parameters X. And we know that for certain values of these parameters. So what is popular now, for example, is a quantum circuit with measurements, for example. So depending on what probability for certain types of measurements, you either have a steady state that's topological or non-topological, for example. But then you just have a single shot for each state you produce. So you have an ensemble. I think you can still parameterize it. I think the question makes sense. I don't know if it actually falls into your theorem, though.
Well, I guess to decide whether it does, we have to see whether that would invalidate the assumption underlying the theorem, which is that a polynomial function of a few body density operators suffices to classify.
That's fine. That's the same thing, because you have the states you get are topological. And if I look at a reduced density matrix of say 4 or 6 sites, and it's more than a 2-side correlation length, then I can probably tell topological from non-topological. But I have just a single axis shot, right? That's the problem. Yeah.
Well, I don't know. I mean, you're going to give me samples of these quantum states. And if indeed there's a classifying function which is polynomial, I'll be able to learn it. If it's polynomial and constant size reduced density operators.
Even if you can only sample once from each state.
One, I don't know what you mean by one from each state. I'm going to measure all the qubits each time.
Right.
Because that's how I make the shadow.
But the next time you get the state, it'll be a different state. You cannot
Right.
repeat on the same state like you can in
Oh, okay, yeah. So no, we can. That still works if you have a big enough
Okay, so
sample
that's
size.
the only issue.
Oh, well,
Right.
actually, wait a minute. I'm not. Now
Yeah,
I'm
I'm not totally sure.
No, sorry. No, it's a good question. In fact, I didn't say this, but what we actually proved is that for each sample, you have to repeat the measurement, some sufficient number of times.
Yeah, I'm pretty sure that's true.
And you think, okay, right. So it's a good question. I should have said this. So you have to sample enough points, but for each sample, you have to, in order to get from the classical shadow a sufficiently good representation,
Right.
you have to predict a sufficient number of times. And in both cases, the number of times you have to repeat for each copy and the total number of samples that you need, those are polynomial in system size. But it couldn't, you have to have enough repetitions of measurements of the same state. Yeah.
Mm.
But a related question, is it a fundamental? Because as you said, if you assume some Fourier space and the smoothness, why do you need to sample multiple times for a single point?
Okay, well, we're talking about two different things now. I think Yehud was asking about the second theorem, you're asking about the first. So in the case where we're trying to learn this, truncated, bandwidth limited version of the classical shadow to predict properties, it is enough to measure once for each sample. But our proof that you can classify phases works only if you measure each of the copies during training a sufficient number of times.
Mm-hmm.
My question is actually related to Ehud's, if I may go next. Thanks, Adam. John, you were very or fairly positive in the end about the potential use of quantum machines for platforms for generating the states needed for classical shadow tomography, as you described. But these are noisy machines in practice, and I'm curious how robust your two theorems are in the presence of finite amount of noise. And it would not just be the stochastic sampling or one shot that Ehud asked, but the kind of realistic noises that we see in as you call the NISQ era machines. I have a second follow-up question on that afterwards.
Well, indeed, this is an important point, and I didn't mention it in the talk for lack of time, but there have been a couple of papers addressing this, including one by Steve Flamia and collaborators. I guess Steve is here. And so what will happen if there's noise in general is that our estimator will no longer be an unbiased estimator. And so we have to, in our inversion of the channel, include some inversion of the effect of the noise. And what other authors, not us, have addressed is that under assumptions about the noise being sufficiently nice, like independent noise, for example, we can characterize the noise well enough to do that inversion and get pretty good robustness of the predictions.
The follow-up, which naturally arises from what you just described, is that your procedure should also work for classical shadows of classical systems, classical stochastic systems, in principle, because the density matrix of those can just be a statistical distribution. But there, it's known to be fairly difficult because of the difficulty of noise. Noise is typically not biased. Noise is typically not well behaved. Do you actually think that it will work in practice?
Well, I don't know. I guess it depends on the noise. We have not, in our work on classifying phases, made any claim about noise robustness at this point. I don't know, I would just have to, I don't have a good answer. I could make an optimistic guess, but you can take it or leave it. I think if the noise is, not highly correlated and that it might not be that different from what I described, which is we just apply some random local circuit to the state, and we can still recognize that it's in one phase or the other. And so maybe it would be fairly robust, but that's beyond the scope of what we've done so far.
Right. Thanks, John.
Cool.
Mhm.
Mohammed, would you like to go ahead and ask your question?
Yeah, it's actually related to the previous question, but more specific. And it's very naive. In the second part of your talk, you showed that the first principal component can tell whether we are in topological phase or not. How can we make sure that actually that component corresponds to the topological order, being present or absent, and not just the artifact of the pristine Hamiltonian that we have implemented?
Well, in the context of the theorem, that followed from the assumption, that this polynomial function exists that classifies phases successfully. In other words, that, it takes a value which is greater than 1 in one phase and less than -1 in the other phase. And then our feature map is designed so that if such a function exists, we can learn it. So maybe what you're questioning is whether to believe the assumption?
Or the assumption, or this principal component that I have now identified corresponds to like entanglement entropy, let's say.
Yeah, well, the point of the principal component analysis was just to illustrate the idea. We don't make use of principal component analysis in the proof. We just make use of the existence of a classifying function with certain properties, and we design the feature map so that if it exists, we can learn it. And I showed the principal component analysis just as a nice way of illustrating, what happens to the distinguishability of the phases as we try to muck them up more and more by, applying local random circuits.
Mm-hmm. Okay, thanks.
Cool. Peter Love, would you like to unmute? Yeah.
Sure. Hi, John. Thanks for a nice talk. You gave a nice example of one of the cases where you needed the measurement data by constructing this factoring example. Do you have any examples where you don't need the quantum device? So where you can do things with classical shadows completely classically?
Well, I'm not sure what the formulation of the question is exactly.
Yeah, so do you know of a subset of states where you can obtain the classical shadows efficiently classically, I guess is the question.
No, I still don't understand, Peter. So is it a question about whether we can go beyond the guarantee that I described for some states that we can describe classically? I mean, if we can describe them classically, then I guess we don't need the classical shadow necessarily in order to predict things about them.
Maybe we can take that
Sure.
or further offline. We should move on to the panel, but before that, thanks, John, for a fantastic presentation. Okay, so let me introduce the panelists as Omid pins up the videos of the panelists. So.